Hello everybody. In this video we are going to be looking at the solutions to the honors electromagnetic induction problems 1 through 5. We've studied electricity and we have studied magnetism. Now we're going to see how those two things are related to one another. So let's start with the first problem. We have a moving rod in the figure is 12.0 centimeters long and is pulled at a speed of 15.0 centimeters per second. If the magnetic field is 0.800 Tesla, calculate the EMF. So this term EMF is electromotive force. And for our purposes and for as deep as we are going to get into this, we can read that the same as a voltage. The only difference in this is that the voltage here is not created by connecting the wire to a power source like a battery, but it is created by moving the wire through a magnetic field. So it is an induced electromotive force or induced EMF. So in this problem, we are given the length of the wire, which is 12 centimeters, which we do need to convert to meters. So that is going to be 0.120 meters. We are given the speed at which the wire is traveling, 15 centimeters per second. And again, we need to convert that from centimeters per second to meters per second. And when I do that, I am going to get a speed of 0.150 meters per second. And the strength of my magnetic field is 0.800 Tesla. And I am being asked to find the EMF, or the electromotive force. And for EMF, we are using this symbol here, which is this kind of funny looking E. It's actually a Euler's constant. Not going to get into what a Euler's constant is at this point. We don't really need to know that. We just use that to specify that is an induced EMF and not an EMF created by connecting the wire to a power source. So we use this instead of the V for voltage, but again, for our purposes, we can treat them exactly the same and they are interchangeable for us at this point, but we just want to differentiate between an induced EMF and one that is created by a power source. So I know that because everything is perpendicular to each other, because if I look at the diagram, I can see that my magnetic field is in the positive Z direction. My velocity is in the positive X direction, and my current is going to be along the Y direction, specifically in the positive Y direction. So everything is opposed to each other by 90 degrees. And each is all on its own axis. So in order to find the induced EMF, I know I need to multiply the magnetic field times the length of the wire times the voltage. And when I plug all of those into my equation, E equals BLV, I'm going to have an induced EMF of 1.44 times 10 to the minus second volts. Okay, everybody, had to take a little bit of a break there, but we are back. By the way, I'm recording this video on Sunday, April 19th, and today, for the first time in I think over 6 years, I actually had to comb my hair. This pandemic is affecting all of us in different ways. My hair hasn't been this long in a very, very, very long time. So, how's it looking there? All right, enough about me. Let's get on to the physics. In problem number 2, we have a moving rod is 13.2 centimeters long and it generates an EMF of 120 millivolts while moving in a 0.90 Tesla magnetic field. What is its speed? So our given values are the length of the rod at 13.2 centimeters, which is equal to 0.132 meters. We are given the induced EMF, which is 120 millivolts. I do have to convert that to volts, so I have to multiply or actually divide that by 1,000, and I get 0.12 volts. And the strength of the magnetic field is 0.90 Tesla, and we are looking for the velocity. So again, we need to use the equation E equals BLV. This time we are solving for the velocity V. So we have V is going to equal E divided by B times L. Plugging in my known values into this equation is going to give me a velocity of the rod of 1.0 meters per second. Problem number 3. In the figure, the rod moves with a speed of 1.6 meters per second, is 30.0 centimeters long, and has a resistance of 2.5 ohms. The magnetic field is 0.35 Tesla, and the resistance of the U-shaped conductor is 25.0 ohms at a given instant. There's a number of parts to this problem, and there is a lot to unpack here. So let's just start and take a look and see what values we are given. We are given the velocity of the rod at 1.6 meters per second. We are given the length of the rod at 30 centimeters, which is going to be 0.300 meters. The resistance of the rod is 2.5 ohms. The magnitude of my magnetic field is 0.35 Tesla, and the resistance of the U-shaped conductor is 25.0 ohms. The first thing that they want us to do is calculate the induced EMF of the conductor, or the rod, I should say. And so because the velocity is perpendicular to the magnetic field, we can get the EMF from using E equals BLV. Don't need to do any rearranging here. It's pretty straightforward. So I know that the induced EMF is going to be the magnitude of the magnetic field times the length of the wire in meters times the velocity in meters per second. And when I calculate that out, I am going to get 0.168 volts, which rounded to two significant figures should be 0.17 volts. Part B of problem 3 asks us to find the current in the U-shaped conductor. So we're looking for current in this part of the problem. I found the induced EMF in the first part of the problem. It's 0.168 volts. And I know the resistance. I'll have the resistance of the conductor at 25.0 ohms and the resistance of the rod at 2.5 ohms. I'm going to need to combine these two resistances together, and now I have the resistance and I have the EMF. I can use Ohm's law to find the current. So solving Ohm's law for current, I'm going to get E equals E over R. Now remember, the E here we can treat the same as the voltage. So they are interchangeable for our purposes here, so that's the same thing. And when I divide the induced EMF by the combined resistance of the rod and the conductor, I'm going to get 6.1 times 10 to the minus 3 amps. Part C asks us to find the external force needed to keep the rod's velocity constant at that instant. There's a couple of key words here. We know that the external force is what we're looking for, and it's keeping the rod's velocity constant, which means that there is a force that's being exerted on the rod by the magnetic field. In order to get the rod to move at 1.6 meters per second, there needs to be some external force acting on the rod to counteract or balance the force exerted by the magnetic field. So if I can find the force exerted by the magnetic field on the rod, then I know what the magnitude of the external force is as well. Because the velocity is constant, that tells me that the forces acting on it are going to be balanced. So to find the force acting on the rod by the magnetic field, I need to use F equals ILB. I am going to just substitute in my value for the current, which I calculated in part B, and the length of the rod, which is given, as well as the magnetic field. And when I do that math out, I'm going to get a force of 6.4 times 10 to the minus 4th newtons. Problem 4. We have a simple generator is used to generate a peak output voltage of 24.0 volts. The square armature consists of windings that are 6.0 centimeters on the side and rotates in a field of 0.420 Tesla. at a rate of 60.0 revolutions per second. How many loops of wire should be wound on the square armature? Let's take a look and see what we're given in this problem. We are given the induced EMF of 24.0 volts. I know the length of one of the sides of the armature, and it is a square. There we go. I don't know what is happening with my pen here, but I'm sorry. There is a square armature. All I wanted to do was circle the word square, and the whole world went wacky. I comb my hair, and the whole world goes to heck. I don't know what's going on here. Sorry about that. All right, so we have a square armature, and I know the length of the side is 6 centimeters, which is going to be 0.060 meters, and the strength of my magnetic field is 0.420 Tesla. The speed at which it is turning is 60 revolutions per second, and because it is turning, it is an angular speed, so we have our omega here for angular speed. I'm going to talk a little bit more about that in a second here. I'm given my speed in revolutions per second, but I know for an angular speed, I'm going to want to convert that to radians per second. I know there are 2 pi radians in 1 revolution, so doing that conversion is going to give me an angular speed of 377 radians per second. And we are looking for the number of loops on the armature. I know that the induced EMF is equal to the number of turns times the magnetic field times the angular speed times the area. Solving that for the number of turns is going to give me N equals E divided by B times omega times the area. When I plug my values in and I do the math, remember it's a square armature, so I just take the length of the side and square that to get the area. I'm going to have 42.1 loops or 42 loops to 2 significant figures. One quick note on this problem, when we were doing circular motion back before the holidays, we were a little bit pressed for time, and we didn't spend a lot of time and go into a lot of detail with angular speeds. I know some of you guys have probably had that in your math classes and you're familiar with it, but we didn't really have a lot of time to go over it, and we kind of glossed over it and just touched on it very, very briefly. I will say, because we didn't really spend a lot of time on it back when we were doing circular motion, on the test, which is going to be next week, I would not, or Mr. Broderick and I will not be giving you any problems that deal with angular speeds on the test. So you won't see anything like this or any problems involving this formula on the test. There's just a little tip for you. Problem 5, another problem that deals with angular speed. We have a simple generator, has 320 loop square coil, 21.0 centimeters on a side. How fast must it turn in a 0.650 Tesla field to produce a 120 volt peak output? So again, we are given the number of turns at 320 loops, the length of a side, and again, we are working with a square. It's a square coil, it should say square armature, but it's a square coil of 21 centimeters. Again, converting that to meters will give me 0.210 meters. I am given the strength of the magnetic field at 0.650 Tesla and the induced EMF of 120 volts. And we are trying to find out how fast this is going to need to turn. So we are going to solve this problem for omega, or our angular speed. Again, using our formula for angular speed, or for EMF, is E equals N times B times omega times area. Solving that for omega is going to give me E divided by N times B times the area. Do the math out, and I'm going to get an angular speed of 13.08 radians per second. So my angular speed is always going to be given in radians per second. I'm now going to want to convert that into revolutions per second, because that's a more familiar term. So to convert 13.08 radians per second, I know that there are 2 pi radians in 1 revolution. That's going to give me a speed of 2.08 revolutions per second, or 2.1 revolutions per second to 2 significant figures.